In this video, we will describe the healthcare application which is developed in DREAMS. It's joint work with STM, and the work starts with ST Body Gateway, where we have a body-worn device from ST, which is able to generate ECG, respiration rate, can be used as a Holter, and it has a Bluetooth 3 connection. On top of this device, we have developed a Linux driver. And this particular driver, we ported into ARM v7 architecture, tested on the Z board, on the Odroid that we will also use in different kinds of scenarios in DREAMS. And in the near future, we will port it into ARM v8, Snapdragon, for example, ST board, and also Juno. The open source ECG analysis is really a soft real-time application that is able for us to detect heart diseases, and we concentrate on the arrhythmia in particular. We focus on visualizing the actual ECG signal first, which is, you can see here the actual ECG signal, and not only that, but we also build filters to detect the bits and classify the bits in the QRS complex. QRS complex gives you the possibility to detect some arrhythmias regarding the repeatance of certain values of the signals. And these repeatance must happen in regular intervals, which cannot be more or less than a given value. The N and V are the different classifications that we will use to annotate our ECG signal and provide a real nice picture of the actual training part of the ECG signal, followed by the actual signal from the patient. So we are able to annotate and provide indications whether there is something problematic. The ECG processing is based, as we said, first on the ST Body Gateway in the driver, then on a conversion to a standard format, then on ECG analysis of this particular standard format, which uses a sample rate of 200, for example, and this analysis is really EC13 compliant and tries to detect and also classify different heartbeats. We focus, as we said, on the QRS complex, and based on previous studies with actual annotations from doctors, we have seen that 99.8% of the normal and ventricular beats that the software discovers have a positive predictivity. So they are actual and false positive. The 3-minute training that we use initially, we have created using ECG synthesis. And really, this ECG should depend on the actual age and the sex of the person who wears the actual ST Body Gateway device. The visualization of the heartbeat is provided to the Wave, which is also a part of the open source chain that we have, and will show also the NMV annotations top of the signal, of the ECG signal. This pipeline that we create here has different lock-ins that refer to files and also semaphores and mutexes in shared memory. And we try also to provide ways to parallelize this part, to do it concurrently and not only in pipeline fashion. And the pipeline also works in both ways because there would be lock-in and unlocking of the files. And we will describe this process also in a little bit. The WFDB, as we said, is a library of specialized signal processing algorithms. It's specified in C with GPL license. It's a successor of the popular MIT database software, and it has been used a lot to analyze physio bank data, which is available in different databases. There are 75 different applications within this WFDB software. We have applications to read and write binary files. We have in different formats. We have conversion in different formats, and we have different types of filters, which are also in the OSEA package. The OSEA is a free toolkit that extends really WFDB functionalities with, for example, filters that use specific algorithms to detect dominant QRS bit detection. Anal bit is another script to allow us to extract bit features, noise check to remove low frequency noise, rhythm check, which is very important for classifying RR intervals, easy test, which we use to detect and classify actually the bits, and create a test type annotation files, which will be used by Wave. There's also a bxbeep function within this API that is very useful for comparing annotation files to provide predictivity statistics for bit detection and classification. This has to do with actually predicting how the software behaves when actually a clinician is involved in the annotation. And this is what we described before with the 99.8% percentage of success of this particular software. The wave part really visualizes the ECG signals and annotations. It has a fast configurable display. It allows backward and forward search for specific annotation patterns, and it provides access in time, forward and backward, high resolution printing, editing the annotations. And very important it is that it provides a remote node so that web browsers can control really the display. The seamless integration of the ST body gateway is very important. So not only we have the driver which configures the body gateway, so it sends messages to really ask the body gateway to send particular ECG signals, for example, or other particular data in a specific fashion. For example, we use ST body gateway with 256 samples per second, but also afterwards we have other threads that do concurrent operations to monitor and transmit data via the Bluetooth that is arriving via the Bluetooth, extract the periodic ECG signal from the raw data, and we also need to transmit the ECG signal via, for example, in our case, a router or TT Ethernet to do time-triggered processing and communication of the data to the actual healthcare application, which is probably running in another place in a server, as we will see later. The seamless integration of the body gateway includes also another part, which is integration of the ECG processing. And the ECG processing really we see as a multiple ECG signal producer merges consumers problem, where as different concurrent threads and processes communicate, and sometimes in pipeline fashion and with locks. So we do local communication, we do remote via shared memory, remote communication via sockets, and we rely on file locking. We will give some more information. The important thing is to watch also the CPU and system performance and energy at the same time to try to avoid overload, and also to try to predict how many patients and how many clinicians can we support with a simple demonstration in a real hospital environment. The ECG generation uses a file locking, and this particular file locking is based on two parts. One part is locking within the body gateway driver, and on the other side to a shared file, because this shared file will be accessed by the ECG analysis process on the other side. So in this case, we save the data into the buffer, and an autonomous agent appends the buffer to a shared file. Then this shared file can be used by concurrent processes that are doing the conversion analysis and visualization. So these are used in pipeline fashion per data per patient. The performance really depends on the number of patients, and we have different viewing options. So these viewing options also affect the actual performance. For example, the ECG conversion, we were surprised that it takes very long. It takes almost 50–55% of the total time, while the ECG analysis, which is usually more demanding, takes only 30 to 40%. So we plan to multi-thread, shared memory, and pipeline customize to actually be able to perform in the best way possible for building a complex system environment within a hospital. So in particular, this environment could include a server, which would be a Juno board, a harmonized platform, which includes the Odroid, which is receiving the signals from the body gateway devices, and these particular data will be moved to the Juno board, where actually we will have the healthcare app running within a particular VM, which we would be able to do all the analysis in time-triggered fashion. So this is the current setup of the final healthcare demonstrator, but I will show you next a demonstrator which is currently developed, as we are not nearing the final demonstration of the project. And we will see this and explain the different parts of the WFTB, the OSEA, and the WAVE. In this demo, you can see the consumer part and the generator part. We will start with the generator part, which will install start the body gateway driver. You can see the data that is received, and you can see the locking mechanism. Then we'll start the consumer, and the consumer will try to process the data and the ECG data, which is extracted from this actual raw data. This particular consumer will try to do all the steps, for example, WR sample, easy test, and XView. Here is the XView environment. You can see the training part, which starts at 0. We have to do several minutes of training, and afterwards you can see the actual patient signal that we receive. In some cases there are movements because the actual device is moving in the body of the patient. The consumer always locks. We can close this interface, open it again, and we will see the continuation of the signal also after the previous signal. So it's in a continuous environment where the doctor can connect to the system, view the annotations, and perhaps we can do also prediction of the annotations and inform the doctor of a special problem in this case. This is the end also of this presentation. I thank you for your attention.